What's up, everyone? Welcome to another video. Today's topic is on balancing chemical equations. When we're looking at a chemical equation, we need to kind of break some things down so that we can really understand what's going on here. Anytime you see atoms or elements or compounds that are on the opposite side that the arrow is pointing, those are going to be the reactants. So the reactants are the substances in the chemical equation that are reacting together. So that should be kind of easy for you to remember that reactants are reacting. And then on the side that the arrow is pointing to, we've got what the reactants are producing, which we call the products. So reactants react, products are being produced. Should be pretty easy to differentiate between those two. There's a couple of other things that we need to pay attention to when we're looking at our chemical equation. The first thing that I want to point out are these numbers that are down below. We call these subscripts. These numbers indicate how many atoms we have of the particular element that they are attached to. So if I'm looking right here, I have O2. This 2 applies to this oxygen, meaning that I have 2 oxygen atoms. Okay, so this subscript tells me how many atoms I have of that particular element that it's attached to. So I would have 2 hydrogens based on this subscript. Based on this subscript, I would have 2. And then if we look at this oxygen here, we can kind of just think of it as having an invisible 1. So there's just 1 O there. But we don't write 1 subscript just because, just simply by having this oxygen here tells me that there's 1 of them. All right, so subscripts, those tell you how many of each atom you have. Now we've also got these coefficients, these 2's in front. These coefficients are a little bit different. We can kind of think of these in terms of like a math equation. So if I'm looking at this 2 in front of H2O, this 2 essentially applies to everything that follows the coefficient. So this would be 2 times 2 hydrogens, which would give me 4 hydrogens. And then this 2 also applies to the oxygen over here, which has this invisible 1 here, remember? So then we have 2 oxygens. Okay, so this total molecule 2H2O, there are a total of 6 atoms, 8 hydrogens. I'm sorry, there's a total of 6 atoms, 4 hydrogens, 2 oxygens. Okay, so just kind of breaking apart the chemical equation to kind of make sense of things before we actually get going on what we're going to be doing today, which is balancing chemical equations. There is a law that we need to follow when we are balancing equations. The law is called the law of conservation of matter. It states that matter can neither be created nor destroyed. So if it can neither be created nor destroyed, whatever I'm starting with is also what I'm going to finish with. So I'm like in my chemical equation, I'm always going to have the same number of reactants as I am products on both sides of the arrow. So I'm always going to want to have, let's say if I have 4 on this side, I have to have 4 on this side as well due to the law of conservation of matter. Okay, so just want everything to be in balance. Think of it as like being a scale. We want it to be even on both sides so that it's not heavier on one side than it is on the other. All right, so we've covered our groundwork. Let's just get into some examples. First, what we're going to want to be able to do is count the number of atoms in a chemical equation. And then secondly, we're going to want to balance the equation using those coefficients that we talked about in order to obey the law of conservation of matter. So let's just go ahead and start with one. We'll take it nice and slow, make sure that we're covering all our ground before we get into some other examples. So when I'm given a chemical equation like this, I see that I have these blanks here. This is where I'm going to want to put my coefficients when everything is all balanced. But the way that I like to tackle this is I first look at my equation, and I'm just going to draw shapes to indicate how many atoms I have just looking at this skeleton right here. So for tin, I have 1, so I'm just going to put an X. I have 2 oxygens here. I'll just put 2 O's, 2 hydrogens, so I'm going to put lines. And then over here, I've got another 1 tin, 2 hydrogens, and then 1 oxygen. Oh, I made it an O on the other side, so I might as well keep it consistent. Okay. So now I've got all my atoms counted, but I see that it's not even on both sides. I have 2 oxygens here, 1 oxygen, 2 hydrogens, 2 hydrogens. That's good. 1 tin, 1 tin. So my job right now is going to be to make it so that I have the same number of oxygens on this side as I do on this side. The only way for me to have 2 oxygens is if I put a 2 in front of this. So the 2 applies to this oxygen, which gives me another oxygen. And then this 2 also applies to my hydrogen. Don't forget, coefficients apply to everything that follows it. So this 2 also applies to this hydrogen, giving me now 4 hydrogens. All right, so looking at this, now my oxygens are balanced. My tins are balanced, but by adding this 2 in front of the H2O, that gave me now 4 hydrogens on this side. So if I want there to be the same number of hydrogens here as there are on and here, then I'm going to need to change this in order to make it be equal. So what can I multiply 2 hydrogens by in order to get 4? Well, you'd multiply it by 2, which would then give us 2 more hydrogens. And we'll go ahead and do some inventory to see if we are actually balanced out. So I've got 1 tin, good. 2 oxygens, okay, good. And then 4 and 4, giving me a total of 7 atoms on this side, total of 7 atoms on this side. So this is a perfectly balanced equation. SnO2 plus 2H2 produces Sn plus 2H2O. Okay, very good. Nice and simple to start off with. We can move on to another one now. All right, so similar layout. Just looking here, everything looks pretty normal. So first what I want to do is I just want to go ahead and count my atoms. So I have 1 titanium, 4 chlorines, 2 hydrogens, and 1 oxygen. Okay, now I'm gonna look on this side, 1 tin, titanium, 2 oxygens, 1 hydrogen, and 1 chlorine. So it looks like I've got some work to do with balancing this. And the way that I like to start is I just like to see which one of these is not equal on both sides. The first one that I come across is chlorine. So I want there to be, if there's 4 on this side, I need there to be 4 on this side. So the only way for me to do that would be to put a 4 in front of HCl, which then gives me 4 chlorines. And now it also gives me 4 hydrogens as well. Okay, that's pretty good so far. So 4 and 4, we're good. But now I've made the hydrogens unbalanced. So I've got 2 on this side, 4 on this side, multiply 2 hydrogens by 2 to give me 4 of them. But this 2 also applies to this oxygen. So now I have 2 oxygens as well. And I'm just going to go ahead and run some inventory really quick to see if everything's good. 1 Ti, okay. 4 chlorines, okay, we're good there. 4 hydrogens, good. 2 oxygens and 2 oxygens. So this is a perfectly balanced equation. TiCl4 plus 2H2O produces TiO2 plus 4HCl. Perfectly balanced. All right, we're going to do one more. And this one is a little bit different than the ones that we've been seeing. So if you look at the past 2, we've only had diatomic molecules. We've only had a tin and an oxygen, or a hydrogen and an oxygen, or a titanium and a chlorine. But now we see that we have Na, we have a sodium, a phosphorus, and an oxygen all in one compound. And over here we've got a hydrogen and a phosphorus and an oxygen all in one compound. So what we're now dealing with are polyatomic ions. And it may look a little intimidating just because we have more letters here to worry about, but there is a little trick to this, and it's going to make it much more simple, and we're going to be able to count it just like we've been doing. So anytime you see that we have 3 elements attached to each other, we know that the last 2 are probably going to be polyatomic ions. So what we can look at these as their own entity. So if we have a PO4, we're just going to count this all as one unit. It's just one thing. So then we could go ahead and count our atoms the same way that we've been doing it without having to worry about all these different types of shapes. We're just going to keep this all as one shape. So I've got 3 sodiums. Let's go ahead and count our atoms. Like I said, PO4, that's just one thing. So we're just going to put a circle there. Hydrogen, 1. Chlorine, 1. All right, sodium, 1. Chlorine, 1. I've got 3 hydrogens, and then remember PO4, we're just counting that as one thing. So I'll just put one circle there. Okay, so then we go ahead, balance like we've been balancing. And what I notice here is I have 3 sodiums, only 1 sodium on this side. So I want to add a 3 in front of my sodium to give me 3 of them. This 3 also applies to this chlorine, so I'm going to put 2 more triangles. Okay, so sodium, sodium, good. Now my chlorines, I have 3 here and only 1 on this side. So I'm going to have to put 3 in front of that to give me 3 chlorines, and that also gives me 3 hydrogens. And I want to go ahead and check inventory. I think I'm balanced here. 3 sodiums, 1 PO4, 1 PO4, 3 hydrogens, and 3 chlorines, and that is good. Na3PO4 plus 3HCl yields 3 NaCl plus H3PO4. So perfectly balanced equation. Now that's 3 examples that you will likely see on a quiz or a test. Hopefully this helps out. If you would like to see some more examples, let me know. Hit the comments below. Until next time, I'll catch you later.